So let's have the derivation of the area moment theorems. So first, let's consider the beam and let's draw the elastic curve, and let's consider 2 points on the elastic curve, namely point C and point D. Then from these points, we draw tangent lines. So we consider a differential element of length differential S on the elastic curve. And the horizontal projection of this ds is denoted by dx, and we learned from the double integration method that the horizontal projection of ds is practically equal to the differential length dx because slopes in beams are usually very small. And I already mentioned in double integration method that usually slopes do not reach 1 degree, and that tangent of angles less than 1 degree is practically equal to the value of 1 degree when converted to radians, so 1 times pi over 180. And take note that that's a given. Also, from calculus, differential x means very small. So, it doesn't matter if the measurement starts at the left of differential x or at the right of the differential x or at the center of differential x. It doesn't matter. So, we draw the typical moment diagram of the beam due to the loadings. So let us say this is the moment diagram, and let's consider portions between C and D only. And of course, the height of this strip, which is highly exaggerated, is equal to m over EI diagram, and that the base is equal to differential of x, which is again very small. So from the left side of this differential S, we draw a tangent line, and from the right also a tangent line. The angle formed between the two tangents is from mathematics, particularly geometry, is also equal to the differential angle theta. And the tangent at C and the tangent at D are drawn, and the vertical deviation of point D relative to the tangent at D is denoted by T sub C slash D, or T sub D slash C, sorry. So the vertical deviation of point D relative to the tangent at C is denoted by T sub D slash C. So the angle here is differential theta, the angle formed between these two tangents of ds, and this is the centroid of this differential strip, and the distance from point D horizontally is denoted by xd. Then this, as I said earlier, that it doesn't matter if the tangent starts at the left of dx or at the right of dx or at the center of dx. They are practically the same because, as I said, dx is very small. So this projection of these two tangents, the intersection with this vertical line here, is equal to, so because it doesn't matter if the distance from the left or from the right of dx, it is the same as x sub d, or from the center, because dx is very small, and we treat this xd here as the radius of a sector of central angle d theta. Therefore, this is equal to radius x sub d times differential theta, and that is differential of t. So that's differential t, and this is x sub d. This is the sector I'm talking about here, and the radius is xd because it doesn't matter if the measurement is from the left or from the right of differential S, because the slope is very, very small. The projection therefore is the same. And the angle between XD is differential theta. So this arc length here, which is equal to or practically equal to this vertical distance here, is differential T, and that differential T is equal to radius XD times differential theta. So we begin with that expression that differential T is equal to XD times differential theta, and we know that differential theta is equal to m over EI times dx from the double integration result, because EI d theta dx is equal to m moment. So therefore differential theta, or the second derivative of y, is the differential of y prime, or the derivative of, or the differential of dy dx is m over EI dx. So therefore we interpret this, if we integrate this, we interpret this as the area of the strip, and we interpret xd as the distance of the centroid of the strip from point D. So deviation of D relative to C is integral of xd times m over EI dx from calculus. So xd is moment arm of the differential area, and dA is m over EI dx, the differential area of the strip. So from calculus, we learned that integral calculus specifically, we have this tool that area times barred x is equal to integral of x sub c dA, and we derive this formula. And also, if we use Varignon's theorem, you can remember this, because the elongated S means summation. So the moment of the area is equal to the sum of the moments of its components, and the component of the area is represented by dA. Therefore, area times x sub d, or the area between C and D under the moment diagram by parts, is simply interpreted as, so this integral here, if we replace xd by x sub c by xd, and we interpret dA as m over EI dx, the area of this strip, and that should be equal to the area under the moment diagram by parts, m over EI diagram by parts, between the 2 points considered, C and D. And this xd here is the distance of the centroid of the area under the m over EI diagram with respect to point D. So particularly, we will call this area under the m over EI diagram as, let's color that with green, and that is actually equal to the angle between the tangents at C and D, this theta CD here. So because differential theta is the area of this strip, m over EI dx, if we integrate that, we simply interpret that as the area under the moment diagram by parts between point C and D. So that's the area of the moment diagram between C and D. So the change in slope between the two tangents is simply the area under the m over EI diagram between those 2 points. And it is equal to positive if the tangent from the left to the right tangent rotates counterclockwise, which follows the same sign convention in trigonometry. That is, counterclockwise rotation is positive. So this shaded green area under the moment diagram by parts is positive, and because this theta CD here is counterclockwise, and it is equal to theta CD. Likewise, if this yellow point here represents the centroid of this green area, then the moment of this green area with respect to this point D here, and we will call that barred XD, is simply the deviation of point D relative to the tangent at C. So deviation of point D relative to the tangent at C is equal to integral of x sub d times m over ei dx, or simply the moment of the moment diagram between C and D with respect to D. And this is positive because the area is positive and xd is positive, and geometrically speaking, it is positive because point D on the elastic curve is above the reference tangent at C. So therefore, we formalize the two theorems by area moment. And the first one is the change in slope between any 2 points on the elastic curve is simply the area of the m over ei diagram between those 2 points. And the positive sign convention is that when the tangent from the left to the right point rotates counterclockwise, then it is positive. Otherwise, it is negative. And the second theorem is the deviation of one point, the vertical deviation of a point, let's say D, relative to the tangent drawn at C, is simply the moment of area between those points C and D with respect to point D, or about point D. So I hope that it's clear. That's the area moment theorems. So that's it for this video. So let me explain the area moment method for this beam here. So we have an arbitrary loading, and we have a load at the right end, a point load, and the simply supported points on the beam AB. So we have AB here is loaded with any loading. So this is the expected elastic curve, and let's draw the moment diagram by parts. For the construction of the moment diagram by parts, it is important to select the moment center because after all, the difficulty that you will encounter will depend on the right selection of the moment center. So here, the best moment center here is either A or B, but B is better for this case. So we select point B as the moment center. So after computing the vertical reactions at A, then we have to sum up moments about this point B. So this is due to the reaction at A. So we have first degree curve, and this is the loading. So this is an nth degree curve in general, and due to the moment of the load P about point B, so we have another first degree curve. So from the definition, this is the tangent at A, then we draw tangent at B. So this is theta AB, which is positive because the tangent from A to the tangent at B is rotating counterclockwise, and counterclockwise is positive. So likewise, if we draw the tangent at C, this is the tangent at C. So from the tangent at B, which is at the left, to the tangent at C, which is at the right point on the elastic curve, rotates clockwise, so that is expected negative. So from this reference tangent A to point B, this vertical deviation of point B relative to the tangent at A is expected to be positive because point B on the elastic curve, which remains at its position because this is a support that does not yield or settle, is above the reference tangent at A. So that's the reason. Likewise, the deviation of point C relative to the tangent at B, because point C on the elastic curve is below the reference tangent at B, which is at the left, is negative. So by theorem 1, the change in slope between tangents drawn at 2 points on the elastic curve is the area between the same points under the M over EI diagram is positive if it rotates counterclockwise. So in this case, the vertical deviation of point B relative to the tangent drawn at A is the moment of area between A and B about point B. So the vertical deviation of B relative to A is expected positive. By the way, the theta AB is positive because from the tangent at the left, which is point A, to the tangent at the right, which is point B, the rotation is counterclockwise. This is positive, and theta BC is negative, of course. Theta BC is the area between B and C, and this is obviously negative. Theta AB is positive because first degree area is greater than any nth degree area if those are the only diagrams that we encounter. So theta BC is negative, as I said, because obviously the area between B and C is negative. Then the vertical deviation of B relative to A is positive because B is above the reference tangent at A. The vertical deviation of point C relative to the tangent at B is negative because point C is below the reference tangent at B. So the sign convention, the change in slope, is positive if the tangents at endpoints rotate counterclockwise, such as theta AB. Then theta BC is negative. Then the vertical deviation of a point is positive if it is above the reference tangent, such as deviation of B relative to A, and deviation of C relative to B is negative. So as another example, we have here, let's draw points here. So call this point 1, point 2, and point 3. So we draw tangents at 1 and 2. So those are the tangents. So therefore, the vertical deviation of point 1 relative to the tangent at 2 would be expected negative because point 1 is below the reference tangent at point 2. Likewise, the vertical deviation of point 2 relative to the tangent at 1 is negative because point 2 is below the reference tangent. And the angle between the tangent at 1 and the tangent at 2 is in clockwise direction, so therefore theta 1, 2 is negative. So that's negative. Deviation of, while theta 2, 3, so this is the tangent at 2, tangent at 3, theta 2, 3 is counterclockwise, so that is positive. Then deviation of 1 relative to the tangent at 2 is negative. Deviation of 0.2 relative to the tangent at 1 is negative. Then deviation of 0.3 relative to the tangent at 0.2 is positive because 0.3 is above the reference tangent at 2. So that's it. Vertical deviation should not be interpreted as the deflection of a point in a beam. The deviation may be the deflection if the reference tangent is horizontal, such as for cantilever beam and one end is fixed. If the tangent at the fixed end is the reference tangent, then that's the only time that vertical deviation of 1 point relative to the tangent, which is horizontal, will be automatic, the deflection. So I hope that it's clear now, so that you can practice solving problems on beams and computing the deflection and the rotation or the slope of a point on the beam.